Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the different region of the spectroscopy or the type of radiation according to the wavelength. And there we have seen there are the four regions depending upon their lambda means wavelength in a nanometer, and there we have seen, if you remember yesterday's lecture, there are the 10 blocks are there. Each block is known as a region: cosmic rays, gamma rays, X-rays, ultraviolet, visible, IR, microwave, radio, radar, TV, and the radio waves or the NMR. So this is a region, and that depending upon their wavelength, if you see cosmic rays, they are there, the wavelength is a very low there, but the energy is very high, and therefore they are harmful rays to the living organism. If you see on a right hand side, there you will see radio waves. The wavelength is very long, but the energy associated with that is very small, and therefore we can carry the mobile radio or we can watch the television very what we can call it as happily. So due to the high wavelength and the low energy, that type of the thing we have discussed yesterday. Today what we are going to discuss here, look at here, interaction of radiation with matter. At the beginning I already told you that the simplest definition of the spectroscopy, what is it? The interaction of electromagnetic radiation with matter is known as a spectroscopy, or the spectroscopy is the study of responses given by the molecule and that are recorded in the form of a graph is known as a spectroscopy. And generally type of the radiation, and when any radiation strike to the molecule, that molecule goes in the excited state, higher energy level, or in the excited state. And when this excited state, whatever amount of the energy and the type of wavelength, it depend upon the structural feature of the organic molecule, and therefore it is essential to study the amount of energy and the type of the wavelength is essential to find out the nature of that, because the final application or utility of this spectroscopy is nothing but to determine the structure of the organic compound, and once you know the structure, it's very easy to predict its physical properties as well as chemical properties. Or other way around, if you know the set of properties, we can easily predict, we can easily determine the structure. So that are the ways. But here the interaction of radiation with matter, molecular excitation. First one is a molecular excitation takes place over here. Molecular excitation takes place over here. So molecular excitation, let us see here how the molecular excitation occurs in the molecule. In a spectroscopy, in a spectroscopic method, the molecule of the matter are exposed to radiation. What happen when radiation strike the molecule? What happen when radiation strike the molecule and what kind of responses are given by the molecule. What kind of responses given by the molecule when radiation strike the molecule absorb part of it, the wavelength or the frequency of the radiation absorbed depend upon the structural feature of the molecules. As a result of absorption of energy depends upon the structural feature of the molecule. As a result of absorption of energy, molecule undergoes excitation, that is, it is raised to higher energy state. The type of excitation produced depend upon the energy of the radiation employed. The type of the excitation produced depend upon the energy of the radiation employed. Number one is a rotational excitation. In a molecular excitation, first we are getting as a rotational excitation. Rotational excitation, when the radiation strike to the molecule, what happen, that molecule goes into as a excited state, and when the amount of energy or the wavelength is absorbed by that molecule, and that depend upon the nature of the structural feature of the molecule, and therefore this type of the excitation is occur. First one is a rotational excitation. What does it mean? Rotational excitation, when rotational excitation is occur, if microwaves are used, lambda is equal to 10 raised to 5 to 10 raised to 7 nanometer, molecule undergo rotational excitation. If microwaves are used, microwaves range, as we know, that 10 raised to 5 to 10 raised to 7 nanometer. If microwaves are used, 10 raised to 5 to 10 raised to 7 nanometer, molecule undergoes rotational, and that molecule undergoes rotational excitation, and this molecule undergoes rotational excitation, right? So that is there. Second one, we can call it as a vibrational excitation. Vibrational excitations. And what does it mean? Vibrational excitation means what? Let's see over here. Vibrational excitations. If infrared radiation, if IR, infrared radiation, as we know that 800 nanometer to 10 raised to 5 nanometer, right? 10 raised to 5 nanometer, this is the range of IR radiation. 10 raised to 5 nanometer are used, they bring about vibrational excitation. As energy of the infrared radiation is higher than the microwaves, along with vibrational excitation, rotational excitation also takes place. Remember here, vibrational excitation means what? When the IR radiation strike to the molecule, the IR range is 800 nanometer to 10 raised to 5 nanometer. When that strike to the molecule goes in the excited state. What kind of the excitation that shows? There is a vibrational excitation takes place, and when the IR radiation has higher energy than the microwave, and therefore along with rotational excitation, along with vibrational excitation, it is associated with the rotational excitation also, and therefore this is it is mean by the vibrational excitation, means you won't get the pure vibrational excitation at all. So along with that vibrational excitation, there is always rotational excitation is occur. So let us look at as a third one is electronic excitation. Third one is electronic. Third one is electronic excitation. Electronic excitations. And what do you mean by again as a electronic excitation? And if radiation from visible and UV region, radiation from visible and UV region, as we know that from visible and UV, that is a 400 to 800 nanometer. This is a range of visible and the ultraviolet rays. From 100 to 800, not from 100 nanometer to 800 nanometer. This is a region known for UV and the visible region. So in that region, and when visible, if radiation from visible and UV region are used, it brings about electronic excitation from bonding molecular orbital to the anti-bonding molecular orbital, as the energy of these radiation is higher than the microwaves and IR. Along with electronic excitation, vibrational and rotational excitation also takes place. Remember here, electronic excitation, when electronic excitation takes place, when the molecule UV or visible radiation strike to the molecule, that molecule shows the electronic excitation. The energy of that visible and the ultraviolet region is a very high as compared to IR and the microwave, and therefore along with electronic excitation there will be vibrational as well as rotational excitation takes place. So this and electronic excitation are occur in the bonding molecular orbital to the anti-bonding molecular orbital. Let us see here, microwave, there is a rotational excitation. In a simplified way we can write microwaves consist as rotational excitation. And if there is a infrared regions are there, infrared region, it consists as rotational excitation as well as vibrational excitations. And last one, visible and UV. Visible and UV, it gives electronic excitation along with vibrational excitation as well as rotational excitation. And fourth one is a translational rotation also there, but we are not going to consider over here. Only three here you can remember. Now is a molecular energy level. What do you mean by the molecular energy level? The absorption of energy leads to different kinds of excitation of rotational, vibrational and electronic energy level in a molecule, and these energy levels of molecule are shown are known as molecular energy level, and these are schematically represented in the figure. Let us see that molecular energy levels, how we can represent this molecular energy level. Let's see over here how it looks. I am going to depict that here on the blackboard. So see here molecular energy level, and just now we know that what do you mean by the molecular energy level. The absorption of energy leads to different kinds of excitation of rotational, vibrational and electronic energy level in a molecule. These energy levels of a molecule are known as molecular energy levels, and these are represented over here. Now I am representing this one. So here I am showing this one. Let us see here along the y-axis here will be energy, and along this side, that is a molecular energy level. Figure indicate that is a molecular energy levels, and which is represent here. I am showing here this one. So how we can show over here? So this type of the levels we can show here. Here we can represent E0, E1. Suppose here is a E0, E1, or here you can again there are some vibrate this electronic excitation, we can call it over here. This is a ground state. Here some of the levels are there like this associated with this. Along this here we can show or we can represent this 1, 2, 3 and 4. There maybe as a this one you can call it as a ground state. That is a ground state electronic levels. This is a ground state electronic levels, and this will be the excited state electronic levels. And you look at this is a electronic excitation, this one, and this one is excited electronics, and that E1, E0, or here also you can call it a E0, and E1 is a excited state along with this. And now along with this there may be this one is a V0, and here maybe as a V1, then V0, V1, here again V0, you can call it as a V1 like this. And now along with that there are R1, R2, R3 like this. I think R1, R2, R3. Similarly here also as R1, R2, R3. Here also R1, R2, R3 rotational. Along with that vibrational there is a rotational compare. Here vibrational we can show like this. This is the energy level diagrams, and then this can goes into as a this type of the excited states like this. It may be like this, or it can be from this it goes into as a excited state like this, or it may be as a shown as a like this vibrational energies. So this is the what we can call it as a representation of the molecular energy levels. So Each electronic level of excitation consists of number of vibrational levels. Second one is each vibrational level consists of number of vibrational level consists of number of rotational levels. For example, E0, E1, E2, etc. represent different electronic levels, and V0, V1, V2, etc. represent different vibrational levels in each electronic level. R0, R1, R2, etc. represent different rotational level in each vibrational levels, and that is schematically depicted in the figure. And we also see from the figure that whenever electronic excitation occur, say from E0 to E1, there will be vibrational and rotational excitation which will accompany. Similarly, whenever there will be vibrational excitation, they will be accompanied by rotational excitation, and thus there can be only pure rotational excitation but no pure vibrational and electronic excitation are possible. The energy separation between different energy levels depend upon molecular architecture, that is the type of atom, number of atoms, types of bond, etc. present in the molecule. This is all about the what we can call it as the interaction of the radiation with the matter we have seen. Now next point we are going to discuss about the absorption spectrum and types of spectroscopy. Absorption spectrum and type of the spectroscopy. So that is the point we are discussing here. We are discussing right now. What is that? The absorption spectrum and types of the spectroscopy. The absorption spectrum and types of spectroscopy that is a point of discussion over here. In the study of spectroscopy, the molecule is exposed to either UV visible or IR or microwave or radio waves. The wavelength of the radiation is slowly changed from minimum to maximum in given region, and the absorption of the molecule at every wavelength is recorded. A graph is then plotted, absorption versus wavelength, and that is represented in the figure. Let me show over here that diagram over here, and this here we are getting such type of the absorption, and this we can maximum we are getting, it is represented as a lambda max. This is a absorption versus absorption, that is represented A versus the wavelength in nanometer. Wavelength in nanometer, that is increased here. So this is a representation of, and here this maximum is getting to 70 nanometer over here, and starting from here 0, then maybe as a 100, 200 likewise. So that is a 360 nanometer, like this nanometers. this type of the graph of absorption versus wavelength is called as absorption spectrum, and this is called as the absorption spectrum. And we see that at a particular wavelength the absorption of radiation by the molecule is maximum, that is there is a peak at a particular wavelength, there is a peak at a particular wavelength, and this wavelength at which there is a maximum absorption is called as wavelength of maximum absorption. Wavelength of maximum absorption, lambda, it is known as a lambda max. We know that maximum, lambda max means wavelength is the maximum at that particular region, and this is the characteristic property of the molecule and belong and help us to elucidating the structure of the molecule, and we will discuss in detail about lambda max and structural relationship in the next chapter. Depending upon the type of the radiation used for excitation, we have different spectroscopic method, and this is summarized in the following table type of the spectroscopic method and how it is shown over here. Let us see that one also. Let us quickly types of spectroscopy. Here we can write as a types of spectroscopy, and in the next column we can write as a radiation used. Here is a radiation used, and in the next column we can write nature of excitation. Here is a nature of excitation. So these are the, let us see here what is happening in the first case, which we are UV and visible spectroscopy. First one is a UV and visible spectroscopy. Radiation used here as a UV and visible. This is the name of that radiation, and nature of excitation are electronic excitation accompanied by electronic excitation accompanied by vibrational excitation plus rotational excitation. So that is the nature of excitation is present over there. And in the next one is a IR spectroscopy. First one, second one is a IR spectroscopy. Radiation used as a IR, and the excitation, vibrational excitation along with rotational excitation, right? And the third one we can write over here, that is a microwaves, right? Microwaves spectroscopy. Microwaves, where we are using as a microwaves, and there is a rotational excitations are there. And the last one, that is a fourth one, is a radio wave NMR spectroscopy here. NMR spectroscopy, nuclear magnetic resonance, and where the radio here used as a radio waves, and the nature of the excitation are nuclear excitation. Here will be nuclear excitations. So I think with this types of spectroscopy, radiation use, and the name of excitation, let us See, once again, UV and visible, the radiation used are UV and visible. The nature of excitation occur electronic accompanied with the vibrational excitation as well as rotational excitation. So that are there IR, then vibrational excitation as well as rotational excitation. Microwaves, there is a rotational excitation only. NMR, radio waves are used, and the nuclear excitation is occur in that. I think with this we have completed this chapter. Let us quickly see over there. There are some of the example how to solve that example. So I think the solved example that we will see in the next lecture. Let us stop today here. Remaining we will see in the next lecture. Thank you. Have a nice day.